Hello, this is Eric from UNC Charlotte. A distributed memory system is a set of computing nodes with their own memory. A node cannot access the memory of another node. The different nodes work together by communicating through a network. Therefore, the question of what each node stores in its memory is important, and the question how to partition the data onto the memory of the different nodes becomes critical. There is typically not enough memory on each node to store the data of the entire problem. And even if that was possible, it would probably be inefficient to move data around that you do not really need. The decision of which nodes store what piece of data is a critical part in the design of a parallel algorithm. The question is not only who does what, but also who knows what. This is where the owner compute rule comes in. The idea is to design the methods so that each piece of data has a primary owner, and that owner is responsible for all the computation associated with the data. How we partition the data, how we decide which nodes owns what piece of data, is the most important design decision in a distributed memory solution. The data partitioning decides memory balance because each node should be able to store the data it owns. It also dictates load balance because allocating the data to a node also allocates computation to that node. Finally, deciding data allocation also forces the communication patterns in the application, since we have already decided where the data is and where it is needed. There is very little leeway in arranging communication differently. This is why the decision of how the data should be partitioned is such a critical decision in the construction of a distributed memory program. Let's take an example to clarify why data partitioning matters. Let's pick a shooting game like Ikaruga or Dodonpachi. You control a ship, they are enemies, and they shoot projectiles at each other. Let's only worry about how the game would detect collisions between different entities using a distributed memory system. The first decision is to decompose the data of the game. Here, that is decomposing the entities and the data associated with them. A simple way to achieve that decomposition would be to randomly allocate an owner to each entity. Here, we show a decomposition in 4 nodes by indicating which node an entity belongs to by coloring the entities in 4 different colors. This decomposition is good for load balancing. We can easily make sure that the different nodes have roughly the same number of objects. But detecting collisions is particularly difficult. The only real solution is for each node to communicate its entities with all the other nodes. So, at every step of the game, each entity will be sent on the network multiple times. Another strategy consists in allocating entities based on where they are in space. Here, we just cut the space in 4 quadrants. This decomposition is potentially imbalanced. The red computing node has many more entities than the blue computing node. But collision detection becomes a lot easier. The red node can check the collision between the red objects by itself, and red entities can only collide with an entity from another node if one of the 2 entities sits on the boundary of a region. Therefore, it is only necessary to communicate over the network the entities that sit on the region boundary. We have here 2 data partitionings of the same problem with very different properties. An entity decomposition balances the memory consumption and the computational load perfectly, but it creates a high communication cost. The spatial decomposition does not balance memory and computational load, but it drastically reduces the amount of communication, so it is likely the preferable decomposition. Most distributed memory applications do not partition the data with rigid rules. Most applications use smart decomposition algorithms to reach a better trade-off between good communication patterns and good load balance. Applications where computations are located in space based on local interactions are often balanced by using adaptive recursive decompositions. Meanwhile, in some applications, the calculations are represented as vertices and neighbors, such as a 3D mesh. These often use complex graph partitioning methods to balance the computation and the communication requirements of the application. It may not be easy to distribute the data and the associated computation beforehand. It is possible that the structure of the data changes over time, or maybe it is not well known in advance. In such cases, we often use dynamic strategies to distribute the load and the data. Manager-worker systems have one node, the manager, send computation to the other computing nodes, the workers. Another strategy is to have each node capable of stealing the work of another node when it runs out. Both these solutions ensure a near-perfect distribution of the calculation, but require significant data movements. They are typically only used when small amount of data can trigger a very large volume of computation. They are used for solving NP-complete problems, for password cracking, or for complex processing algorithms of multimedia data like face recognition in videos. When trying to rebalance data in computation while the application is running, the problem is often to ensure that the cost of rebalancing the data is worth the benefit of having a more balanced distribution. The distribution of the data of an application onto the nodes of a distributed memory machine is critical. The owner computes rule implies that data partitioning dictates load balancing and communication patterns of an application. It is important when designing a distributed memory application to choose carefully a data partitioning strategy. Ideally, it has good properties for balancing the volume of data, balancing the volume of computation, and to minimize the amount of communications.